Welcome everybody, you're watching Mr. Fugu Data Science. Today we're going to do NumPy basics for Python newbies. I want to mention something to you. Please look at this right here, okay? That'll be valuable in your life and your career. You just need a couple installs real quick. These are going to be pretty simple and painless. If you don't have NumPy, do a pip install or a conda install. Depending on your situation, you may need to do pip 3. There's a couple things I want to mention with why you should use NumPy. One, you can use it for logical or mathematical operations, but the fact that if you're dealing with regular old Python lists, this can slow you down if you're trying to do computation such as looping. Things like this can be problematic if you have a lot of data. That's where NumPy can help you out, because in the background it's using C or C++ and it's storing your arrays in one location. Whereas a Python list, it's not going to store it in one contiguous location. You are able to use vectorized code with NumPy, which allows you to avoid explicit looping. And behind the scenes is using that C compiler. Now, since you're using vectorized code, you're able to compact this in your memory, okay? And one of the other issues that Python has is type checking. Python uses dynamic type checking. So at runtime, when you run your code, then it'll start evaluating to figure out what the type is for everything. One of the caveats that you have to notice is that when you use NumPy, you need the same data type. Python lists could have mixed data types. You could have some ints, you could have some strings, you could have whatever. That's one thing you need to pay attention to. I want to show you, for comparison with speed, two examples where we're going to run the size of 1 billion. First, we're going to go through a list comprehension, which is faster than a regular for loop, and then we're going to compare it against a NumPy array of the same size. We're going to do some multiplication here for our list while we're iterating through and do a NumPy multiplication. And you're going to notice something right here. When you run this, it may vary on your machine, but you're going to see that speed up of 10 times. That's quite a bit. There's ways that you could run this and actually make it even faster using Numba alongside with NumPy. And if you wanted to make it even faster, you could also work with the C compiler using Cython. We won't cover those today. The next example I want to show you is going to run through a few different examples. Let's get into what those are. I'm not going to show this code. You could pull it off of my GitHub because it's quite lengthy. So if you're dealing with concatenation, dot products, scalar addition, or deletions, you can notice a few things. We're not quite 10 times as fast doing the concatenation. The dot product, on the other hand, is more than 10 times. We have quite a bit in scalar addition, and if we're making any deletions. So this is another step towards going in the right way of using NumPy for some of your operations, especially if you're a data scientist or data analyst or someone who's doing computational work. Also consider SciPy. Now, we can do conditional operators, for instance. We can use this arrange. Let's see what this is doing. First, you're creating an array from 0 to 11 where it's 12 entries, okay? And we're looking for something that's greater than 9. We could also do multiple conditional statements and throw those in as well. The first one, when we're looking for greater than 9, it's returning a Boolean value, whereas the second one is returning a actual value. Just like if you're throwing this into a data frame and doing some conditionals the same way. Just depends on how you're actually calling this. If you're just calling the array, it just returns a true and false. If you're returning the array like this, then it'll return similar to if you had a Python call for your data frames. You can do various indexing as well. We could set up array in descending order or a regular ascending order where I'm doing a step size of 1 and I'm going reversed. We can pull 2 through 6 exclusively, which means that we're going to negate the 6th one. We can go through the elements 1 through 8 in steps of 2 and return those. And you can also do specific values that you want to pull. For instance, you could pull the 4th element twice, the 2nd and the 9th one. And these are index positions, okay? We could look at 2D and 3D arrays for indexing as well, where we could throw in our array and we're going to take the second element of the first dimension or first array. So this is the first array that we're dealing with, the first dimension, and we're going to take the first element that's inside of there, which just happens to be 1 here. We could do the same thing and look for the sixth element of the second dimension, which would be here, and we'll take the second one, or pardon me, the sixth element of that here. Doing the 3D one gets a little tricky, so you have to figure out where you're going. We're first going to go into this, pay attention to the notation. So we're first going into this one, then we're going to go here, which is this part, and then we want the second one, which is out of there, which is this one. Remember, these are all by indexes. You can also do some importing and exporting of files. You could load text, you could generate from one file type and convert it to another. You could save the text, just chuck in your file type that you have here, your array, and then if you have a delimiter, for example. We can inspect the properties. These three you'll use quite often to figure out what's going on. You can convert your data types just like you can with a data frame. If you had to change a column, you can convert to a list just like you would do for a data frame. You could do the same type of thing, and you could figure out what's going on with something in particular if you just chucked it in to the parentheses. You could do linspace, which is giving you the ability to create intervals within a range, where we're going from 0 to 3 and we want 6 items printed off and they're evenly spaced. We could create what's also called a copy or a view. If you're making a copy, you're making a new array. And if you make any changes to that copy, it will not affect the original. The view is just like what it's called. It's just a view. Now there's something you can pay attention to. You can verify for yourself if you've never seen this before, if indeed your array, your copy versus your view will own the contents of what's here. And when you print this out using this dot base for your copy and your view, you're noticing that that copy does not own that array. We have reshape, which is very useful because there's situations where you need to change the dimensions of your data. For instance, we just have this 1D array and we want to reshape it into 2 dimensions, where we're going to have 2 rows and 2 columns, okay? You're originally starting off here, where your rows are 4, but you just have 1 column and you're converting it. We can do sorting with various algorithms here, depending on what you need. You have to pay attention, but you still have the axis, which is 0 or 1 as well to do your manipulations. So let's look at our array that we have right here, okay? And we notice that we have these 2 rows, 4 columns. And if we do a merge sort based on our row, you'll notice that this now becomes ordered and so does this, okay? Well, that seems kind of odd because it's a 1, not like in a data frame where it's a 0. So you have to pay attention to how that actually works when you print this and see what's going on. Here's the reverse if we're working with the columns. These were in order, except this one, the second and third column, or pardon me, the second column and the first column were changed from this original right here. We can add and remove elements if we need to. For instance, we have our array that we have right here, this 2-dimensional array, and we want to add this in, and we're doing it row-wise, okay? We can also delete, for instance, if we wanted to delete based on the index position of 1 for our column, we're dropping this right here, this 977 or 12. You can do the same thing, but go row-wise, where basically we dropped the first row right here. You can get more specific, and you can drop the first row and the third row, which means we're just left with the middle row. Now you can use something to change your dimensions using squeeze or expand. Expand allows you to add a new axis, a row or a column, depending on what you're needing. Squeeze is the opposite, but is very distinct because you will shrink it only if the axis has a single entry. This single entry is extremely important, okay? For instance, if we have this shape, the single entry for the shape means this and this. You could choose the 0 axis, the second axis, but you cannot use this first one because it does not equal 1. Let's look at this example real quick, okay? So we have this multi-dimensional array and it's 4 dimensions. We decide that we're going to use the squeeze. We're going to use it on axis 0, 1, and 3. We cannot use it on axis 2 because we'll get an error in this case. Now, pay attention to something. Notice when you print this off, the amount of brackets you have. Okay, this is the original 4D. To the next spot where we're going to 0, we're going to go in 1 layer and take it away. Now when you go to the axis equals 1, it looks like the same thing again that you're printing off. But let's get a little more specific and see what's going on here. So we're going to look at this and get the shape of it so it makes a little more sense. We have 1, 1, 4, and 1. Okay, fine. We're going to take away for axis 0 this one. That's what's going on is you're left with this. Axis 1, you're taking away this one. That's why these two look the same. And then axis 3, you're removing this one. And this is what you're left with. Okay, they're all 3 dimensions. And you have the same amount of elements. They're size 4. So breaking this down could help you visualize what's going on because it could get quite confusing adding dimensions to your data. Now the expand. So we have this 1D array. We're going to work with our columns. And we're going to work with our rows. Okay, let's look at what this is. So let's print this off and we have our 1D array, which is 5 rows and just our single column here, our original data. Now we changed this to work along the columns and now we'll have a 1 by 5. So we rotated this. We can go along the rows and rotate this into a 5 by 1 because you notice there's nothing here. Okay, well that's fine. We can look at basic mathematical concepts. I'm not going into the whole list of these. The things you're probably going to be more interested in are the linear algebra things that come up with matrices because you could do an identity matrix, okay? You can do matrix of all zeros, all ones, change up the size of the matrix that you need. You could do anything with random values. For instance, you could do random integers. You could do sampling. Just depends on what you need. I'm letting you just see what is available to you. There's various sum operations that you need to pay attention to. For instance, you could sum along a 5 by 5 matrix, which is from 0 to 25, and you could sum everything together to get this value. You could get the column sum, where you're summing along axis 0, and then you can get the row sum. So you have to pay attention to what you're doing, because that can mess you up later, okay? You can use something called flatten and ravel. Flatten gives you a deep copy. If you use regular Python in your first course, your first few courses, it should cover something about shallow and deep copies. Your deep copy is creating a new ND array in memory, okay? So any changes that you make will not affect the original. The shallow copy is using a pointer for the memory location and anything you do will change it, okay? So let's have our 2 by 2 of all ones and let's flatten it out and see what happens. So we have our shape, which is starting with a 2 by 2. It's 2 dimensions, size 4. It gets flattened out into a 1-dimensional array, okay, that you see right here. That's the deep copy that we're using with the flatten. We can do the same thing, but with ravel, making our shallow copy. The formatting is still the same. You just do dot ravel to whatever your NumPy array is. Nothing else goes in there. It's easy. And you'll notice it's doing the same thing, going from 2 to 1 dimension, except you have a shallow copy. You can run different statistics. Here's an idea of some of the basic things that you can do. Only distinctions, pay attention if you're using the argmax versus max. One gives you a max value, the other one gives you an index position for that value. We can use stacking and concatenating, for instance. You can increase the rows, you can increase the columns, you can also create a third axis, throwing this into 3 dimensions, and we could do something similar to concatenating if you're looking at regular Python. Okay, so let's create 2 arrays with these values and do a VStack, okay? But what's really going on with this? Well, the VStack is allowing us to create rows, okay? Let's see what these look like. Okay, so this is just one row and it's getting chucked in with the other row after it. The reverse, we're making a bunch of columns and it's only one row, okay? The third option is using this DStack, which is going to create our 3D object. We have 2D arrays here. So we have 2 of these 2D arrays that we're going to convert into a 3D. Let's look at this, okay? So let's pay attention to something. Since these 2 arrays right here are equal in size and shape, we're going to print off the fact that they're in 2 dimensions. And this is what we're dealing with for the first one, A of 2D. Now, if we combine these together, you're going to notice that we're doubling the size and we're increasing the dimension. So now we have a 3D object. And that's what's going on here. Notice the number of brackets that you're dealing with. The other thing that we need to consider is to concatenate. And that's just like if you were similar to doing concatenation in data frames, very similar, you throw in the axis, we're going row-wise, and we're putting both of these together. Just remember to do the parentheses, okay? And that's what's going on here. Here's the first one, here's the second one. Easy enough. we're saying that we're starting with this 2 by 2, which is 2 dimensions, and there's only 4 items for each one of them. After we concatenate, we're still keeping the same dimensions. We're just adding rows, okay? So that's what's going on. You're just adding the rows to it for the way we set it up with axis equals 0. Axis equals 1, doing the same thing, you're going to add columns. That's what's going on here. So we take the same thing, we change the axis to 1, and we pluck out 4 columns instead of 2. Okay, cool. So that means that we added these 2 and these 2. We can think of doing an extension onto a list if we're iterating in regular old Python, and you can use axis equals none, and it just makes one big old list, or pardon me, array, okay? So if you notice, here's our 1D array that we have now, which is 8 items. You can use something that's very useful called broadcasting. There are some limitations with this I suggest you look into, but it's allowing you to do arithmetic operations on arrays of mismatched sizes. This is done by stretching the smaller array to fill the void. It will basically wrap around the values in the smaller array to make it match the size of the larger. But you need to consider something, this right here. To make this work, either they need to be the same size or one of them needs to be 1. Otherwise, you get a value error. Let's see what's going on with this. So we have an array that's a 1D array of 4 elements. We have a 2D array with 4 elements each. We add them together, that's fine, because we're starting with the same sizes that we're going to put together and end up with a 2 by 4. That's fine. We expand this and move a little further where we're dealing with a 2D and a 1D object, where we have a 4 by 3 and we have a 3 item. And what happens here? We can still add these together because we still got these 3s that are jiving with this, so we can make our 4 by 3, okay? This is doing element-wise addition, okay? So this element with this element with this one with this one, and then the same thing, this one with this one, and so on. But this do something with some mental gymnastics is going to throw you for a quick loop if you don't pay attention. You got your 1D, you got your 2D, you got 6 elements in here, you have a 2 by 4, but you got an issue. Let's say we transpose this real quick and we try to fix the dimensions to try to make this work. I decide to add a NumPy array of zeros that's a 2 by 6 onto this. So instead of having a 6 by 1, now I have a 2 by 6. Okay, cool. We do a transpose of this and we end up with a 6 by 2 by 1 here because we're using something new called a new axis. All right, we're adding that in so we can increase the dimensions and use these data because we need either everything to be the same or have a 1. And that's what's going on here. So what I did was I took the new value that I needed for the shape, and I wanted to show you that if we're taking the shape of B, we have a 2 by 4 and a 6 by 2 by 1. And we end up with the result of a 6 by 2 by 4. So you're using this and you're using this. So we're taking a 3-dimensional object, adding it to a 2-dimensional, and ending up with a 3-dimensional result. That's what we get from this. That's how we can move a 1 dimension and 2 dimension end up with a 3 dimension, starting with a 6 by 1 and a 2 by. So it's really confusing, but I suggest watching this again to see what's going on because something like this will probably come up in your life. The next thing, we could take the same thing we had before and we could do element-wise multiplication. Works out. And remember, these are the outer products that we're dealing with. The next thing we could deal with is the inner product with the dot product, using the same thing but doing a transpose on B that I did instead, so I could show you that this works as well. But I just wanted to do a quick rundown so you get some ideas. It was kind of fast. That's why you have to pause the video. Go back, look at the code, see what's going on. This is just a primer, but I hope this brought utility to someone. Please like, share, and subscribe. And if you subscribe, turn on that notification bell. I would like to say thank you to the recent subscribers and viewers. I greatly appreciate it. Don't forget, I started a Buy Me a Coffee. Shameless plug, but I need to. I spend a lot of time on these videos, and if you decide to help out, I'd greatly appreciate it. I'm also on Instagram and Twitter. Look for those in the link in the description below. Thanks. Have a good one. Bye.